Hi friends, today we are discussing about flexibility matrix method of analyzing a continuous beam. In this we are firstly dividing the steps. First step includes determining static indeterminacy. Whatever the beam is given, we'll first determine the static indeterminacy of that. And in step 2, we'll identify the redundant forces. That is, we'll write the number of coordinates. Displacement at the redundant coordinates is statically determinate in statically determinate structure due to applied load is to be found. Firstly, we'll take the given statically indeterminate beam with the loading conditions already mentioned in the question. So to this beam, we'll just determine the displacements at the redundant coordinates. So in this method, we are using conjugate beam method to determine the displacements at the redundant coordinates. Next, in step 4, we'll find out the displacements or developing flexibility matrix by applying unit force in the redundant coordinates. Firstly, we are just taking the beam with the given loads. In step 4, we'll not consider the given loads, we'll just apply some unit force and we'll see all the forces, that is displacements, developed because of this applied unit force at the redundant point. Okay. Next, if we are talking about delta 1 1, the first one will represent the coordinate at which we are finding out the displacement, and second one would represent the load application, the point at which the load is applied. So it is delta 1 1 means at 1 we are applying the load and we are seeing the displacement at that one point because of the applied load at 1. Okay. Next, so let us solve an example. This is the given continuous beam for us carrying UDL in first span and central point load at the second span. First step is determination of degree of static indeterminacy. So degree of static indeterminacy can be determined using this formula. ds is equals to r minus 3, where r is the reactions for the given continuous beam. To understand this more better, please view beam video in my channel, because there I am explaining the reactions to be considered at each support. So for fixed beam we'll have 3 reactions, and for roller beam we'll have 1 reaction, and again we'll have 1 reaction. So in total we have 3 plus 1 plus 1, that is 5 reactions. 5 minus 3 will give 2. 2 is the degree of static indeterminacy. Next, we will just assume 2 as the redundant forces. Okay, so second step is identifying the redundant forces. So we are thinking the moment at A and moment at B as redundant forces. So we are considering MA and MB are redundant forces. Now in step 3, I told you we'll be taking the given loading conditions and we will be calculating displacements at this point, that is the coordinates we have considered. We have taken MA and MB as the redundant forces. So we'll just apply, see, this is the given condition, the given loading condition in the question. So for this we'll be calculating displacements. So in this sum we are using conjugate beam method. So for conjugate beam method, remember under point load we will be getting a triangle one, and under a UDL one you will be getting a parabola. So here the triangular one, the vertical height of this is WL by 4. So we are taking it as simply supported beam. For simply supported beam with central point load, the bending moment, the height of this is WL by 4. And for UDL, it is WL square by 8. Here the W is 30 kilonewton. So 30 into L is 6 meters. It is in 6 meter span. So 6 square by 8. And next we have central point load. It is WL by 4. W is 80 into 4 by 4. WL by 4. So we'll get the moment. The height of this will be known. So in conjugate beam method, the area of this first part, the parabola, would give us this part, that is the redundant force at section 1, whatever we assumed, that is MA, is equal to area of the first part, that is area of the parabola. we will take the centroid of this, like this will be half of 2/3 of base into height. Area of this parabola, we know the formula, that is 2/3 of base into height. The height is known, the base is nothing but the length of the beam. So 6 into height is 135, we got this. So this is 270. Half of this delta 1L is equals to half of this area divided by EI. Okay, next, the second one, the redundant force we assumed. So the displacement delta 1L from moment of area of M by EI diagram measured at A for beam AB. So for beam AB, the span AB, we are taking it as delta 1L. So to calculate delta 2L, that is area, the delta 2L, that is at this point. So to calculate at this support, like at this force, at this redundant force, that is equals to this span. So we'll just add both of this, that is half into 2/3 of 6 into 135 by EI plus half into base into height. Half into base into height is the area of this. Okay, but we are just dividing it by 2. So both AB and BD spans would give us delta 2L. This is delta 2L. So the displacement delta 12 from moment of the area, that is M by EI diagram measured at B for beam AB and BD is 350 by EI. So the last step we have here is getting the stiffness matrix. Stiffness and calculation of the flexibility matrix. So here we have delta 11. Delta 11, that is both at the same nodes. You are applying the force at this same node, and calculation of this flexibility or the displacement is at the same node. So here it is L by 3I. When both are different, it would be half. We carry over factor would be half of that. That is L by 3I into 1 by 2. That is dividing this. That is equally L by 6EI. So delta 11, when both are equal, it would be L by 3I. When both are different, it would be half. The carryover factor, half is transferred to this. So here we are dividing it. It is simply L by 6EI. Okay. So delta 11, that is at this point. This let us see what all the members that are connecting to this point. Only the member AB is connected to this. So it is simply L by 3I of AB span. When we are taking L21, that is 21. So we have to take a member that is in between both 1 and 2. Again we are taking only AB span. But when we are taking 2, this is center one. So we have to consider both. So see, to this support both AB span is connected, BD span is connected. So we will be taking both L by 3I of, see, as both are 2, we will take 3I. As it is in between of AB and BD, we will take both spans. Next, when we are taking 1, 2, that is both are different, the carryover factor will come. So it is L by 6I of span AB, because L 1, 2 is in AB span only. That is half is transferred to 1. Okay. So the next, flexibility matrix method. So for flexibility matrix method, we would be taking delta 11, delta 12, 21 and 22. Okay, this is the matrix. See, we know this. Okay, we got all this. We will simply substitute in this. We know all is in EI. So we are taking 1 by EI common in this. Okay. So delta is equals to delta L plus delta R. That is delta L plus, we know the delta right, that is this one is P into deflection. That is the load applied into this. So when we need these loads, that is this will become inverse, and this is the external loads applied at the joints. See, if we are taking the moment as redundance, if there are already any moments mentioned at that particular support, we will take here in this case. But here we are not given any movements acting at that. So external loads are not present. This would be 0. It is simply this one. So remember, this is the formula. Okay. So 1 by EI of this delta is flexibility matrix we have got. Okay. This is the flexibility matrix, that is inverse. And as this is 0, minus would be there, minus 1 by I of delta L, that is the given loading conditions we have calculated by conjugate beam method. Okay, so this is the simplification. We are calculating the inverse first and we'll be giving this. We can also do it directly in the calc. So we'll get the loads at that. That is, these are the redundant forces. First we have considered. These are the redundant forces. So the next step is the redundant forces we have calculated. We'll be applying to this diagram. We'll just divide the spans into span 1 and span 2. We'll just apply the redundant forces we have calculated, also with the loading that is given in the question. Okay, now we'll take summation Fy is equals to 0, that is upward loads Ra, Rb1 is equals to downward loads. Downward loads, that is 30 into this span 6 UDL. So that is the reaction, and we are taking moment about A, that is Rb1 into 6 is plus 97.06 kilonewton meter. As it is already moment, we are not multiplying it with any distance. Next, the UDL, that is WL square, 30 into 6 into 6 by 2, the centroidal distance, plus this moment 75.58. So we'll be getting Rb1, and using this expression we'll get Ra also, the reactions. Next, taking the BD span, that is second span, moment about B2 is equals to 0, that is Rd into 4 plus 75.88 would give me Rd, and using summation Fy is equals to 0, I will be getting Rb2. So we'll be calculating all these values in this way. After this, we'll draw shear force diagram and bending moment diagram. Shear force diagram, by just applying these loads, I will explain you. See, this is the span A, B, and this is D. This is C. Okay, this is the span. At RA, it is going upward. That is 93.53 kilonewton. It is going upward. And because of this load, we are subtracting 30 into 6. So this would become 86.47 downward. And again at RB, we have 2 points. That is RB1 and RB2. Because of RB1, it would go 86.47. That is, from here, it would go to 86.47. Okay, so RB2 again 58.97. It will go a bit upward. Okay, some from here to here we have no loads, it will be stable, and again it will go 80 downward. 80 downward means 21.03. It would be constant, and at RD we have 21.03. Again it will go that upward. So this is shear force diagram, this is bending moment diagram. This is it for this video. Thank you for watching the video. Please like, share and comment the channel if you like the content. Thank you. Thanks for watching. Please like, share, comment to my channel. Please subscribe to my channel. Thank you.